Hello, dear students, and welcome to the e-content lecture series of mathematics. In this video, we will discuss the topic concavity or convexity of a curve. In our earlier classes, we have already discussed about the maxima and minima of a curve y is equal to f of x. And also we studied the intervals where the function is increasing or decreasing. To be precise, we studied f of x is increasing if f dash x is greater than or equal to 0, and the function f of x is decreasing when f dash x is less than or equal to 0. Also for maxima or minima points, f dash x equal to 0, these points are also called as critical points. For further classification, if f dash x changes its signs from positive to negative while crossing over the critical points, then point is a maximum point, that point is a maximum point, and vice versa. Here on the same lines, we shall study the points of inflection of a given curve and the intervals in which the function is concave upwards or concave downwards. So let's start with the definition of concavity and convexity of a curve. A curve is said to be concave downwards, or we can say that convex upwards on the interval, open interval a comma b, if all the points of the curve lie below any tangent to it on that interval. And it is said to be concave upwards or convex downwards on the interval AB if all the points of the curve lie above any tangent to it on that interval. Here note that a curve convex upward is called a convex curve and a curve convex downwards is called a concave curve. You can see the figure on your screen, where in the figure 1 you can check that if you have the given curve y is equal to f of x, then you will draw the tangent on that curve. You can easily check that all the points of the curve lie above the tangent to the curve. So this curve is called as a concave upward curve. And in the figure 2, you can easily check that if you draw the tangent on the curve y is equal to f of x, then you can see that all the points of the curve y is equal to f of x lies below the tangent to the curve. If all the points on the curve lie below the tangent, then the curve is called as a concave downward curve. And if all the points of the curve lie above the tangent to the curve, then in the figure 1, you can check that the curve is concave upwards. And the figure 2 shows that the curve is concave downwards. Now, we will discuss the definition of point of inflection. A point that separates the convex part of the curve from the concave part of the curve, that point is called as the point of inflection. You can check the point of inflection on your screen. There you will find the red dot on the screen. This red dot is called the point of inflection because that point separates the concave curve from the convex part of the curve. This point is called as the point of inflection. Now we will discuss the working methods to find the concavity and convexity of the given curve. Uh, if you have given the curve y is equal to f of x, first of all you have to calculate the second order derivative of the function y with respect to x. That is, you have to find the d2y by dx2. Then you have to find the interval, that is a comma b interval, for which the second order derivative of the curve is greater than 0. Uh, then the interval AB, open interval AB, is the interval of being convex downwards, for which the second order derivative is greater than 0. Similarly, for the interval AB, for which the derivative d2y by dx2 is less than 0. Here there is a typing mistake. You have to check the interval for which the second order derivative is less than 0. Then the interval AB is the interval of being convex upward, for which the second order derivative is less than 0. Now we'll discuss the working method to find the point of inflection. In this case too, you have to find the first step, second order derivative of the given curve, that is d2y by dx2. Then you have to find the values for which the second order derivative is equal to 0, and also the values of x, if any exists, where d2y by dx2 does not exist. So when you check the d2y by dx2 is equal to 0, there you will find the points, say a, b, c. These are the possible points of the inflection. Then one by one you have to check the possibility of the points of inflection. Suppose we have to check the point x equal to a will be the point of inflection or not. Now, for this you have to first check d2y by dx2 either changes signs at that point, or you can check that the third order derivative exists. Here again there is a typing mistake. You have to find the third order derivative, and you have to check that at that point the third order derivative is not equal to 0. By two methods you can find the point of inflection. Note that d2y by dx2 is equal to 0 is not a sufficient condition for the graph of the function to have a point of inflection. So we will discuss these definition: concave upwards, concave downwards, and point of inflection by some examples. So first of all, consider the curve y is equal to e raised power x for all x belongs to R. Here there is a typing mistake. You have to check the curve y is equal to e raised power x is concave upwards for all x belongs to R. So solution of the first is, first of all, you have to check that the curve is e raised power x. Then the working method to find the concave upwards or concave downward is that you have to find the second order derivative of the function with respect to x. And we know that the second order derivative of the exponential function is again e raised power x. And we know that if we put uh, x is any real number, if we put any x belongs to R, you will check that the second order derivative is always greater than 0, because exponential function is always greater than 0 for every real number. So you can see that here the curve is concave upwards because the second order derivative is greater than 0 for all x belongs to R. So you can say that for every x belongs to R, the curve, given curve y is equal to e raised power x is concave upwards. Now we will discuss the case where the curve is concave downwards. Second example, here the given curve y is equal to logarithmic function of x, and we have to check the condition for concave downwards for which x is greater than 0. Um, Step 1 is you have to find the second order derivative of the function with respect to x, and we know that the second order derivative of log x is equal to minus 1 by x square. And you can easily check that if we put any x greater than 0, d2y by dx2 is always less than 0. If you put x any value greater than 0, there you will find that d2y by dx2 is always less than 0. So the second order derivative is less than 0 for all x greater than 0 means that the given curve is concave downwards, or you can say that convex upwards for all x greater than 0. Here x is greater than 0. Actually there is a typing mistake. So so let's discuss the next curve or next function y is equal to x raised power 1 by 3. uh, for this curve you have to find the points of inflection. So first step is to find the point of inflection is that you have to find the second order derivative with respect to x. And if we differentiate twice the given function x raised power 1 by 3, we will get minus 2 by 9 x raised power minus 5 by 3. And we know that here the d2y by dx2 does not exist when x is equal to 0. So for the point of inflection, we check the condition whether for x equal to 0, d2y by dx2 changes signs or not. For this, you have to put the values of x less than 0. Then you will find that d2y by dx2 is greater than 0. And for x greater than 0, d2y by dx2 is less than 0. So it means that the second order derivative of y with respect to x changes sign if we take x less than 0 and we take x greater than 0. Or you can say that d2y by dx2 changes signs at x equal to 0. So here x equal to 0 is a point of inflection. Or you can say that 0 0 is a point of inflection of the curve x is equal to x, sorry, of the curve y is equal to x raised to power 1 by 3. So thank you so much. God bless you all.